Federated learning faces a significant challenge in accommodating clients with varied computational capacities, hindering the participation of resource-constrained clients in global model training. To address this issue, federated importance-aware submodel extraction, FIARSE, dynamically adjusts submodels based on the importance of model parameters. FIARSE constructs a submodel by sequentially incorporating parameters in descending order of their importance levels, from highest to lowest, until the client's maximum computation capacity is reached. The proposed approach overcomes the limitations of previous static and dynamic submodel extraction methods, enabling dynamic updates of submodels that capture the evolving nature of model parameters. In contrast to rolling-based submodel extraction, FIARSE adaptively identifies important parameters, ensuring outstanding performance for both the global model and local submodels. FIARSE converges at a rate of 0.1 square root t, consistent with state-of-the-art Florida algorithms, and outperforms existing approaches, particularly on clients with limited computational resources. The Model-Heterogeneous Federated learning problem is formulated, where each client has a distinct computation capacity. The optimization problem involves optimizing the model parameter and the client's masks, which represent the submodel extraction. A preliminary solution, partial averaging, is presented, involving sampling a subset of clients, local model training, and global model aggregation. However, previous approaches, such as FLADO and p-Fed-gate, require significant storage and computation costs. FIARSE explores the correlation between the value of model parameters and their importance levels, allowing for simplifying the problem by selecting larger parameters to build the submodel. The novel submodel construction method jointly selects and optimizes model parameters, reframing the problem by controlling the number of parameters included in the submodel. The TCBGD algorithm integrates straight-through estimation to calculate the gradient in the backward propagation, forming a biased gradient descent that considers the importance levels of model parameters. FIARSE, a federated learning algorithm, integrates a threshold-controlled biased gradient descent method to address model heterogeneity. The algorithm updates parameters greater than or equal to a designated threshold, reducing computation costs and accelerating the update of parameters near the threshold. The server extracts a submodel based on parameter values and sends it to participants, who utilize local training with TCBGD to optimize the local model. The aggregation process on the server side updates the global model via partial averaging, aligning parameter values with their importance levels. The convergence analysis of FIARSE is established under non-convex objectives and model heterogeneity Florida scenarios with partial client participation, relying on assumptions of masked L-smoothness, bounded global variance, and masked reduction. The authors establish bounds between local objectives and the global objective, considering noni, I.D. data, and define assumptions to characterize the masking performance. Theorem 4.4 presents the convergence result of FIARSE, with a detailed proof provided in Appendix C, showing that the convergence rate is bounded by a term that approaches zero as the total communication rounds tend to infinity. Corollary 4.5 provides a specific setting for the local and global learning rates to achieve optimal convergence properties. Experimental results demonstrate that FIARSE outperforms other methods in terms of test accuracy, showcasing superior performance as more clients achieve higher accuracy. The results are presented in Table 1 and Figure 2, evaluating the performance of FIARSE and other baseline methods on 3 datasets under different submodel sizes. The experimental setup involves a combination of computer vision and natural language processing datasets, with a ResNet-18 architecture and a pre-trained Robert-to-base model. FIARSE, a model-heterogeneous federated learning algorithm, is proposed to extract submodels of various sizes through importance-aware operation. Experiments on ResNet-18 and Robert-to-base demonstrate its superiority over state-of-the-art methods, leveraging model sparsity supported by some hardware. Performance evaluations on the global test dataset show FIARSE consistently outperforms baselines, including Hetero-FL, Fed-Rolex, and Scale-FL, across various submodel sizes. Figure 3 presents the test accuracy trend throughout communication rounds, highlighting FIARSE's superior test accuracy with fewer rounds. Table 1 shows FIARSE achieves at least 2% better test accuracy on CIFAR 100 and AGNEWS. FIARSE is also evaluated on unparticipated clients, demonstrating its effectiveness in extracting submodels of different sizes. Figure 4 shows FIARSE outperforms baseline methods, particularly when extracting smaller submodels. A comprehensive survey of federated learning research highlights techniques for improving communication efficiency, addressing non-IID data, and leveraging sparsity. Model pruning, knowledge distillation, and sparse training are discussed as methods for addressing challenges in federated learning. Key papers, such as Fjord, Topcast, Scale FL, and Depth FL, are highlighted for their contributions to the field. The survey emphasizes the importance of sparsity in federated learning, citing papers like Sparse FL and Lottery FL. Non-IID data is also discussed, with papers like 17 and 35 addressing its effects and proposing solutions. Optimization algorithms, such as FED-AVG and convergence analysis, are discussed as crucial components of federated learning. The section concludes with a discussion on limitations and future directions, including the need for more efficient communication protocols and methods for addressing non-IID data. Future work includes investigating neuron-wise importance-aware submodel extraction and developing more effective methods for model-heterogeneous Florida. The literature review on federated learning, knowledge distillation, and personalized model training highlights recent advances in these areas. Studies have explored heterogeneous model architectures, partial client participation, and resource-adaptive learning, addressing the objective inconsistency problem in federated optimization. Personalized federated learning approaches, such as heterogeneous model reassembly and personalized federated learning for edge clients, have also been proposed. Theoretical convergence guarantees for resource-adaptive federated learning with mixed heterogeneity have been established, and anchor sampling for federated learning with partial client participation has been explored. Optimization techniques, including latency-aware optimization, have been investigated to improve the efficiency of large-scale machine learning models. The importance of efficient optimization techniques is highlighted in the context of federated learning. Model customization and sparsification are two approaches to facilitate model heterogeneity in federated learning, but existing works on model customization require a shared public dataset. The proposed approach, FIARSE, eliminates the need for a public dataset and explores the correlation between model parameters' importance levels and their values. Equation 3 is derived, involving the partial derivative of the model output with respect to the input, and Theorem 4.5 is proven, providing a theoretical foundation for the proposed approach. The aggregation process is defined as the weighted sum of local updates from selected clients, and the lemma shows that the global update follows a specific form. FIARSE is compared to existing works, such as FLATO, and is shown to reduce overhead on clients and make it more suitable for resource-constrained devices. Equations 611 and lemma C.1 provide a mathematical formulation of the proposed approach, illustrating its effectiveness in facilitating model heterogeneity in federated learning. Here is a combined summary of pages 17-20. The authors introduce a vector partition scheme across different sizes, as shown in Table 2, which defines submodels and participation sets. This scheme is used to derive an expectation equation, 14, involving the local learning rate A to L and the number of clients NA. Preliminary lemma C.2 establishes an upper bound for the expected squared difference between the local model and the global model, assuming assumptions 4.1, 4.2, and 4.3 hold, and the local learning rate satisfies a certain condition. The bound is derived by recursively applying inequalities, 1624, which involve the gradient of the local model and the global model. The authors then derive a series of inequalities, 2530, to establish an upper bound for the expected squared difference between the local model and the global model, which is a function of the local learning rate, the number of clients, and the norm of the global model. Another lemma, C.3, establishes an upper bound for the expected squared difference between the gradient of the global model and the gradient of the local model, assuming assumptions 4.1, 4.2, and 4.3 hold, and the local learning rate satisfies a certain condition. The authors then analyze the convergence properties of the FIARSE algorithm by deriving a series of inequalities to bound the term $math BB E tilde x underscore t plus 1 tilde x underscore t squared underscore $2. They apply the Cauchy-Schwarz inequality to obtain equation 38 and equation 39, which are then used to derive equation 40. By applying the Cauchy-Schwarz inequality again, they obtain equation 44 and equation 45, which are then simplified to equation 46 and equation 47, using assumptions 4.3 and 4.1, respectively. Finally, they apply lemma C.2 to attain equation 49. The authors present lemma C4, which states that under certain conditions, the FIARSE algorithm satisfies the inequality $math BB E tilde x underscore t plus 1 tilde x underscore t squared underscore 2 lec 8 eta squared underscore s eta squared underscore lk squared frac a delta squared underscore t tilde x underscore t squared underscore 2 plus nabla f tilde x underscore t squared underscore 2 plus sigma squared $2. The proof involves using the recursive function of the global updates of FIARSE and bounding the term $math BB E tilde x underscore t plus 1 tilde x underscore t squared underscore $2 using equation 52 to equation 54, and analyzing the bound for $math BB E nabla x caret I underscore t kf gamma underscore j1 gamma underscore j squared underscore $2 using equation 55 to equation 60. Here is a combined summary of pages 21-24. The proof of theorem C5 establishes the convergence rate of FIARSE for non-convex objectives, assuming assumptions 4.1, 4.2, and 4.3 hold. The theorem defines the local learning rate eta L and the global learning rate eta S, and derives the convergence rate by bounding the expected difference in the global objective function f between two consecutive iterations. The proof applies the L-smoothness of the global objective function, bounds the expected inner product of the gradient and the update direction, and uses the definition of the global update rule. Lemmas C1 and C.2 are employed to simplify the expressions and obtain the desired bound. The final bound, equation 81, shows that the convergence rate of FIARSE is 0.1 square root t, where t is the total number of communication rounds. An experimental study on federated learning with heterogeneous models is presented, focusing on the impact of different submodel sizes and participation rates on test accuracy. The experiments are conducted on 3 datasets: CIFAR10, CIFAR100, and AGNEWS. The hyperparameter settings are listed in Table 3, and the authors evaluate the test accuracy of 4 federated learning methods: HeteroFL, FedRolex, ScaleFL, and FIARSE, under different submodel sizes and participation rates. The results show that FIARSE outperforms the baselines by at least 7% and 3% for CIFAR10 and CIFAR100, respectively. Ablation studies on CIFAR100 demonstrate the flexibility of FIARSE in accommodating varying numbers of complexity levels or client distributions. Figures 57 illustrate the performance changes of various strategies for submodel extraction in terms of test accuracy versus communication rounds on the global test dataset. The authors highlight the importance of considering system heterogeneity in federated learning, demonstrating the effectiveness of FIARSE in accommodating varying model sizes and participation rates. The proposed method, FIARSE, demonstrates superior performance on CIFAR10, CIFAR100, and AGNEWS datasets, achieving up to 2% improvement over existing baselines. Figures 6 and 7 illustrate the model performance of various model sizes over communication rounds, showcasing FIARSE's significant outperformance, particularly with small submodel sizes. This highlights the method's effectiveness in scenarios where the submodel is applied to the global dataset. Ablation studies examine the effectiveness of TCBGD and threshold selection strategies. The first study compares TCBGD to pruning greedy, which selects the largest values at the beginning of local training and keeps the mask unchanged. Results emphasize the necessity of optimizing model parameters based on their importance, as merely optimizing parameters without considering their importance is insufficient. The second ablation study investigates different threshold selection strategies, including layer-wise and unbalanced approaches. Results indicate that preserving a fixed ratio of parameters for each layer, as in the layer-wise approach, leads to a balanced but inferior structure. In contrast, preserving more parameters in the initial layers while discarding later layers, as in scale FL and hetero FL, yields better performance. This suggests that more parameters should be preserved in the early layers, while later layers may have redundant parameters. These findings highlight the importance of optimizing model parameters based on their importance and the need for a balanced structure. FIARSE's superior performance can be attributed to its ability to optimize parameters based on their importance, leading to more efficient and effective model compression. The results also underscore the significance of carefully selecting threshold strategies to preserve essential parameters while discarding redundant ones.